Okay, friends, very good evening. Today we are again going to discuss about RF integrated circuits unit 2 review of mass device physics. Okay, what are the basic concepts involved in this topic or mass device review distributed systems. Second topic transmission lines, reflection coefficient, the wave equation and examples, lossy transmission line, Smith charts, plotting gamma, bandwidth estimation using open circuit time constants and bandwidth estimation using short circuit time constants, uh, rise time and rise time and rise time and delay and bandwidth, high frequency amplifier design, zeros to enhance bandwidth, shunt series amplifiers, tuned amplifiers, and cascade amplifiers. So, what are the symbols of, first of all, what are the symbols of MOSFETs? So, here uh, NMOSFET symbol and PMOSFET symbol. NMOSFET symbol is like this and PMOSFET symbol is like this. Okay. So N MOSFET symbol is B connected to ground and B here P in PMOS B is connected to VDD. B is connected to VDD. Okay. So here are the two symbols of the MOSFETs. So MOSFETs are used mainly in the IC technology. Okay. MOSFETs are used mainly in the IC technology that P substrate and diffusion regions, source, drain, and gate are connected like this in matter. Bulk substrate or bulk or substrate. Okay. So, what are the two junctions formed here? So, what are the two junctions formed? S to B, source to body and drain to body, or body to source and body to drain. Okay. Here are the two junctions formed. Here we are taking P substrate which is lightly doped and we are taking N diffusion regions, and the region between the N two diffusion regions is placed with SiO2 region is coated with the dioxide, and then the metal plate is placed, and after that metal plate the gate surface is connected. Okay, the gate surface is connected. So here P substrate is like this: body, substrate, source, gate, drain, oxide regions. Okay, gate, drain, and oxide regions. These are the substrate, source, gate, drain, and oxide region. So P substrate is located. The length L is located between the two diffuser regions. Two diffusion regions. So, what are the points? Review of MOS device physics. So, a basic N-channel MOSFET consists of two heavily doped N-type regions, the source and drain, which constitute the main terminals of the device. The gate was made of doped polysilicon material. The substrate is a lightly doped P-type material. The substrate is also called bulk and is at the same potential as the source. A basic N-channel MOSFET consists of two junctions. Let us assume that there is zero drain to source voltage. Next, as an increasing positive voltage is applied to the gate, holes are progressively repelled away from the surface of the substrate. At some particular value of gate voltage, the surface becomes completely depleted of the charge. Further increase in gate voltage induces an inversion layer composed of electrons supplied by the source or drain that constitutes a conductive path between source and drain. When the gate to source voltage is several kT by Q above Vt, the device is said to be in strong inversion. The induced inversion charge is proportional to the gate voltage above the threshold and the induced charge density is constant along the channel. The induced inversion charge is proportional to gate voltage above the threshold, and the induced charge density is constant along the channel. Let us apply let us apply a positive drain voltage, then the channel potential must increase from 0 at the source and to VDS at the drain end. The net voltage available to induce an inversion layer therefore decreases as one approaches the drain end of the channel. This is the overview of mass device physics, and the block diagram is and the structure or the structure of n-channel MOSFET is like this. Okay, and n-channel MOSFET. So n-channel MOSFET also we have already known the operation and also the description of mass device. Hence, the induced charge density varies from a maximum at the source to a minimum at the drain end of the channel. The channel charge density has the following form. Qn of y is equal to minus COX of VGS minus V of y minus Vt. Qn of y is the charge density at position y. COX is equal to epsilon Ox by Tox. V of y is the channel potential at position y. The linear or triode region of operation is defined as one in which VGS is large enough to form an inversion layer. From our expression for the channel charge density, we see that it has a zero value when the charge VGS minus V of Y minus VT is equal to 0 at drain end, and VGS minus VT is equal to 0. That is VDS is equal to VGS minus VT. So drain current in the linear region. Here in this, the drain current is proportional to charge times velocity. Hence, ID is equal to minus WQ of Y nu of Y. The velocity is simply the product of mobility and electric field. Hence, ID is equal to minus WQN of Y mu N of E, where W is the width of the device. Substituting now for the channel charge density, we obtained ID is equal to minus WCOX of VGS minus VT. VGS minus VT. The velocity is simply the product of mobility and electric field. Hence, ID is equal to minus W Q n of y into mu n of e, where W is the width of the device. Substituting now for the channel charge density, we obtained ID is equal to minus WCOX of VGS minus V of y minus Vt into mu n of e. The electric field is a negative gradient of the voltage. ID is equal to mu n Cox W Vgs minus V of y minus Vt into dV by dy. ID into dy is equal to mu n of Cox into W Vgs minus V of y minus Vt into dV. Now integrate along the channel and solve for ID, that is 0 to L. ID into dy is equal to ID into L is equal to 0 into VDS. Mu n Cox W into Vgs minus V of y minus Vt into dV. Then ID is equal to mu n Cox W by L into Vgs minus Vt into Vds minus V square ds by 2. Note that the relationship between drain current and drain to source voltage is nearly linear for small VDS. Thus, a MOSFET in the triode region behaves as a voltage controlled resistor and the drain current in saturation region. So, substitute VDS is equal to PD sat in above expression to drain current saturation region. So ID is equal to mu n Cox into W by L into Vgs minus Vt into Vd sat minus V square d sat by 2. Then ID is equal to mu n Cox by 2 W by L Vgs minus Vt whole square. The transconductance of such a device in saturation is easily found from differentiating our expression for drain current. Then Gm is equal to mu n Cox W by L into Vgs minus Vt, which may also be expressed as Gm is equal to square root of 2 mu n Cox into W by L into Id. As the drain voltage increases, the depletion region's width increases and effectively shortening the channel. Since the effective length decreases and hence the drain current increases, this effect is known as channel length modulation. So, as the drain voltage increases, the depletion region width increases and effectively shortening the length. Since the effective length decreases and hence the drain effect is also called channel length modulation. To account for this effect, the drain current equations for both triode and saturation are modified as follows. That is, ID is equal to 1 plus lambda into VDS into ID node, where ID node is the drain current when channel length modulation is ignored. The parameter lambda is a semi-empirical constant whose dimensions are those of inverse voltage.